Hi everybody, welcome back. This is Unit 4 for Regents Chemistry. This is video 9, and today we're going to be talking about the weirdos, the groups 3 through 11, or in some textbooks it's considered 3 through 12. All those really low guys on the periodic table, which are known as the transition metals. So we're talking about this group here, the low guys. Now this has identified 3 through 12. Sometimes it's 3 through 11. It really just depends on the textbook that you're looking at, okay? These are the metals that you know are metals, like nickel and copper and silver and gold and platinum and iron. These are the things that you think of when you think metals, but actually these are pretty unreactive metals. They're not as reactive as the group 1 and group 2 metals, okay? Which is why we know about them. It wouldn't make any sense to make a necklace out of sodium, because the minute that necklace got wet, it would react and produce hydrogen gas and a base, right? Sodium hydroxide. So then you'd no longer have your necklace. But it does make sense to make a necklace out of gold, because gold does not react with water. In fact, gold does not react with many things. It's a very, very unreactive metal, okay? You probably wouldn't want to make a necklace out of iron, though, because iron will rust. Iron will react with oxygen, and it'll create iron oxide, which wouldn't be as pretty, I suppose. So anyway, these are generally not very reactive metals, these weirdos. What makes them weird are a couple things, or what makes them unique, I guess, instead of weird, are a couple things. Number one, when you have ions of transition metals, for example, you have iron ions or copper ions, they actually produce solutions that make colors. Sodium doesn't do that. Like if you have a solution of salt water, it's not a pretty color. But if you have a solution of iron chloride, it is orange. It produces this pretty color here, okay? It's orange. And because it's a transition metal, and that's what transition metals do. They make colored ions in solution. This is what copper ions look like in solution. They're beautiful blue, right? Copper is blue. And then I have some cobalt here. Cobalt is another weirdo transition metal. And cobalt, depending on the temperature, can either be pink or blue. So this cobalt is pink, this solution, okay? So transition metals make colored ions in solution. Okay? Copper is blue. Iron is, I guess you'd call that like an orange. And that's why when something rusts, you have that orange color. That's the iron ions that are creating that color. Okay? So transition metals make colored ions. What else is unique about transition metals is if you look in their boxes on the periodic table, and I'll show you that real quick. Okay, so here we are, and if you look at the group 1 metals and the group 2 metals, like if you look here for lithium and here for magnesium, they only have one possible charge in their box. They can only have an oxidation state or a charge of +1. So when sodium's happy, it can only be +1. When magnesium's happy and stable, it will only be +2. But look at titanium, and look at vanadium and chromium and manganese and iron and cobalt. They have multiple positive charges there. They are the only area on the periodic table, the only region where you will find elements with multiple positive charges, the transition metals, okay? So that is another unique thing about them. There we go. Recording. So what we can say is that they have multiple positive oxidation states. They have more than one possible positive charge in their box. That's what that means. The reason for that is that most metals, other than them, they only lose their valence electrons. But the transition metals can actually lose electrons from two shells. They can lose electrons from their valence shell, like everybody else does, but they can also lose electrons from their next outermost shell. So whereas most metals will only lose from their outer shell, these guys will lose from two shells. And so really what that translates to is that happiness really isn't 8 for them. Okay, they can be happy with a valence shell with a number of electrons in it other than 8. Okay? So that is our weirdo transition metals. They make colored solutions, they have multiple positive charges, and they can lose electrons from two shells. Bye, William. The next group we'll talk about is group 15. Group 15 contains a variety of elements. If you think about this is our list of group 15 elements. We have nitrogen in there, which you can't see. Nitrogen, you still can't see it. Phosphorus, I'll do it over here. Arsenic, antimony, and bismuth. And the stairs intersect this group right here. Like arsenic is on top of the stairs and antimony is below the stairs. So when you look at this group, the first two members of this group are nonmetals. Nitrogen and phosphorus are nonmetals. The next two members of this group are semimetals. These are metalloids. They have properties of both metals and nonmetals. And the final member of this group bismuth, is a metal, okay? As you proceed down the group then, their nonmetallic character decreases. They become less like nonmetals, but more like metals. When they use that language, nonmetallic character, it means the properties and behaviors of nonmetals. And metallic character would mean the properties and behaviors of metals. So as you go from nonmetals to metals, it only makes sense that they become less nonmetallic and more metallic, right? There is one of our diatomics. Remember, our obsessed Cleveland Browns fans have no intelligence. We have one of the diatomics in this group. It's nitrogen. And nitrogen is triple bonded to itself. So it'll make 3 bonds to be happy. If you think of nitrogen, it has 5 electrons in its outer shell. So it will need 3 more to be happy. And however many more you need to be happy, that's how many bonds you will make. So since nitrogen needs 3, it'll make 3 bonds with itself. And it's incredibly stable molecule that way. Super stable. Like, that is why our body can't utilize it. We breathe in, most of what we breathe in is nitrogen, but we can't do anything with it because it's strongly triple bonded to itself. So it's very stable and happy that way when it's triple bonded. All right, that's it for tonight, everybody. Have a great night. We will see you tomorrow, and we'll get a little bit further in our discussion of metals and nonmetals. You'll do a lot of practice tomorrow. Don't forget, it's the first due date for your SPY secret agent periodic table. Talk to you later. Bye-bye. Hi, everybody. Welcome back. This is Unit 4, Lesson 10. And we're going to talk about 2 other groups on the periodic table that you have to know more than just general trends about, and that the first one of those is group 17, which is highlighted here in red. That's group 17. And then right next to it, we'll also be talking about group 18 today. So you need to know their name and then some specific things about them. The group 17 elements, fluorine, chlorine, bromine, iodine, are known as the halogens. They are group 17, and if you recall, the last number of the group is how many valence electrons they have. So they have 7 in their outer shell already. And if you recall, happiness in your outer shell is 8. So in order for fluorine or chlorine or bromine or iodine to become stable, if they have 7 in their outer shell, they just need to gain 1 more to be stable. And if you gain 1 electron, since the electrons are negative, you will have a charge of -1 when you are an ion. They are excellent because they are nonmetals at attracting electrons. And what that means is that it's very hard to take away their electrons. So they have high ionization energies. It requires a lot of energy to remove their valence electrons. And they have high electronegativities. They're very attractive. They attract others' electrons well. These are the most reactive nonmetals on the whole periodic table. And the reactivity of nonmetals is opposite the reactivity of metals. Their reactivity decreases down a group. This is a very important point, okay? So with metals, we said the biggest metals are the most reactive. With nonmetals, it's opposite. The smallest nonmetals are the most reactive. Okay? These are so reactive, all of them in group 17, that you, like group 1 and like group 2, you cannot find them in nature in their elemental state as pure elements. They only exist as stable compounds. And they are the only group on the periodic table that contains elements in all three phases of matter. Fluorine and chlorine are gases. Bromine is a liquid. And iodine is a solid. And this group also has 4 of our 7 diatomic elements in it. If you remember our diatomic elements, obsessed Cleveland Browns fans have no intelligence. Cleveland Browns fans' intelligence are all in this group. So F, fluorine, chlorine, bromine, and iodide are 4 of the 7 iodine diatomic elements, which means they exist as 2 atoms stuck together in their elemental state. The final group we have to talk about on the periodic table are the group 18 elements, and these are called the noble gases. They used to be called the inert gases. They have 8 in their outer shell, group 18. They have 8 valence electrons in their outer shell, except for helium. Helium only has 2. But remember that the first shell is full with 2. These elements are very stable because they all do have a full outer shell of electrons. And they do not react in nature. But there are a few that have been forced to react with oxygen and fluorine in a laboratory. And you can tell which ones have been forced to react because they have oxidation states other than 0. They have charges other than 0 on your reference tables. But I believe they are xenon, krypton, and argon have been forced to react with fluorine and oxygen in a lab. So these middle 3 right here, they've actually been able to make compounds out of those, and some of those are used for refrigeration. So the noble gases are what all the other elements aspire to look like in terms of their outer valence shell of electrons. Okay? That's it for today, everybody. Have a great night, and we'll see you in class tomorrow. Bye-bye.